U3 lesson 7. As usual, you're looking for the tasks to complete for U3L7. You can find it under assignments or on the Canvas homepage. Today's date is December 2nd. We are officially in the Christmas season. Instead of starting off by throwing you into breakout rooms to answer a random question, I wanted to start off by collecting some feedback from you. I meant to do this earlier. I'm sorry I haven't, but first thing you should do is fill out the December 2020 Science 2 course feedback Google form. This is completely anonymous, so please take your time. I appreciate honest answers. I have no way of knowing who wrote what, so be as honest as you want to be. So take your time to complete that. I'm going to time for 10 minutes to work through it. I'm hoping it won't take that long, but we'll just come back together once it looks like most of you have it done. If you do finish really early, you can move on to the next item, which is a formative assessment probe. But for now, focus on the feedback survey. Go for it. Let me know if you need help. Hi, Kayla. These two that we've done. So looks like 7 of you went with the boiling temperature did not change. It's funny, this is identical to the previous class. Option A. 1 of you went with option B, which is the boiling temperature decreases, and 3 of you went with C, the boiling temperature increased. So interesting. The most correct answer is indeed A, and that's something we're going to explore today. It's due to something called latent heat. But again, those of you who chose otherwise, there are a lot of misconceptions around this, chiefly the letter C, right? People thinking that if you've got water on a stove and even if it's boiling, if you keep heating it, it's just going to keep warming up. It's actually not what happens, and it's kind of interesting what's happening on a molecular level there. But good job. Looks like most of us are in a good place to address that. Before we move on with that, though, I wanted to just quickly review the homework. You had the PhET simulation to complete. We did most of it in class, but again, I've seen 14 responses. So it looks like most of you were able to finish that up afterwards. The Hewitt homework assignment's also looking good. Again, a couple answers off. I'm seeing 12 responses to this. I remind you again that if you did get a few things wrong, you have up to 10 attempts on this to get that perfect score. So don't be afraid to retake it after you kind of look through like what you got wrong, and then you know to focus on those questions. So any questions or comments on those homework assignments? Alrighty. First thing we're going to do then is a little activity relating to that formative assessment probe that you just did. In that formative assessment probe, we had a student who was continually heating water. And so now on the tasks to complete list, we're on step number 4, heating curve of water. I'm going to show you some actual data from that. If we had been on campus in the laboratory, you would actually do this experiment. We would have hot plates and beakers with ice and thermometers, and you would warm the ice all the way to boiling and measure the temperature change over time. What I'm doing instead, if you click on that assignment right there, heating curve of water, it will take you to this assignment. It's a Canvas quiz, I think. Yes, sorry, I just have the stats showing here. But it'll walk you through what to do. You're going to open up another Google Sheet where I actually already have some data ready for you. So this should be pretty simple. You just need to make a copy of it like we've done in the past. And then you're just graphing this data here. It's looking at the heating time and how the temperature changed. And so I kind of walk you through in the assignment what I did. If I can just hit preview here real quick. So you have to imagine that this is what we would have done in the laboratory. I like the pictures that are right here. This is the setup, right? You would have had ice in a beaker with a thermometer in it on a hot plate, and we would have heated it all the way from ice to boiling water, and you would have measured the temperature. So that's what that data is. So you just need to graph it, and then there are some questions to answer on the quiz related to the graph that you make. You're also going to submit your graph as a shared link to that first question. I'll be here listening if you need help. I'm going to time for 15 minutes to work through this. But again, we'll come back together once it looks like most of you are done. Let me know if you need help. 15 minutes to work on the heat curve for water. Takeaway thing to emphasize there. So any questions or comments on that little quiz? All right, you all ready to be guinea pigs? I'm trying out a new program here. just trying to find new ways to present slides and information to you and get questions quickly. I know we've been using like slides and poll questions, but now I want to use a website called Nearpod. And I meant to do this in my previous class, but has anyone ever heard of or used Nearpod before? Oh, okay, let's see how this goes. Okay, in my previous class, but so on the tasks to complete list, what you need to do is just click on the link right below step number 5, vapor pressure and boiling point, where it says Nearpod vapor pressure and boiling point. Should take you to a website where it's going to ask for a join code. It's going to ask you to join a lesson. I'm going to start the lesson right now. Sometimes it takes a little while to load, so give it a minute to think. But then we should be good to go. All right, the join code that you need to enter is JV9PX. Just like with Kahoot or quizzes, you have the opportunity to enter your name. Please just use your name or something close to it so I can see who everyone is when you're answering questions. I'm gonna post the join code to the chat as well so that it stays there. So I just put the join code into the chat. If you need to see it, it's right there, JV9PX. See how we're doing. Seeing 7 people registered so far. Again, there are 12 of us here, so let's try to get 12. And then we can get started. All right, let's get up to at least 10. See, 9 people joined. There we go. Yeah, I know this might be loading a little slowly. It seems to move slower. All right, we're at 11. Great. Okay, so this program is kind of like Edpuzzle, but for slides. So I'm able to work through slides with you and then present questions to you all within the same program and can show you right answers and things like that. One thing I'm curious about is if I can use the annotate feature through Edpuzzle. So is everyone seeing the phase changes in front of them? Yeah? Okay, can you see me writing on it? Like, did you just see me circle phase changes? Yes, okay, cool. Well, these, I don't know if these were meant to work in conjunction, but it seems like they do. So, all right, so we're just picking up where we left off, right? We were talking about 3 states of matter, solid, liquid, and gas. There is a 4th one, plasma. But what I want to focus on again is just remember that heating should be associated with melting and vaporization. We're exciting molecules, giving them more kinetic energy, and cooling takes us in the exact opposite direction. How many things do I need to click on here? It's going to get annoying. Well, so as you saw in the formative assessment probe, the most correct answer to this situation, if you brought water through boil and kept on heating it, the temperature would actually not change. It would stay at 100 degrees Celsius. And this is because of what boiling point actually is. So my goal with these slides is to explain how we scientifically define boiling point, because it's going to be very specific and it explains why this happens, why you have these pause points in temperature change. So this is a sort of cleaner version of the graph that you made using the data from the Excel sheet. And again, it's just showing you heating time on the bottom. So this is heat being applied. And then you've got the temperature change. And so clearly, this again, I think is for water. You can assume this is H2O. And so no surprise, right? It warms up, it warms up, warms up. But then once you hit 0 degrees Celsius, you hit this weird pause point. And that's because the energy is still being supplied, right? We're still heating it. But what that energy is now doing is converting all of the solid particles into liquid form. So that's why you have that pause point. That's where the energy goes. So rather than increasing the temperature, it's changing the state. Once it's all liquid, once there's no more solid left, once that's all gone, then it can warm up again, right? So then we see this rise, and again, it hits this pause point at 100 degrees Celsius because now all the energy is going into converting those liquid molecules into gas. They're all escaping. And only once everything's turned into a gas, once there's no liquid present, then you'll see the temperature rise, right? If you were to somehow take the temperature of the vapor, it would be higher than 100 degrees Celsius. So here's just the heating curve with the labels, which I kind of like. So it shows you that those plateaus, those flat points are the melting point or freezing point, depending on whether you're heating or cooling. And likewise, then at 100 degrees Celsius, you have the vaporization point or condensation point, again, depending on whether you're heating or cooling. But again, the reason it pauses there is because that's where the energy, rather than being put into changing the temperature and exciting molecules more, it's changing the state, releasing them as gas, and so on. So the key point is that we refer to this as latent heat. This is an important vocab word to get down and be familiar with. That just describes the energy put into these pause points. So it's energy that was applied, but did not change the temperature. Instead, it was changing the state, right? So it does not change the temperature. Instead, it is used to change the phase or the state, going from solid to liquid or liquid to solid, going from liquid to gas or gas to liquid. That's the key point from that first part there. So here's the first question to present to you. You place a beaker of liquid water with a thermometer in it in a freezer and watch the thermometer change over time. You notice the temperature of the water drops gradually until it reaches 0 Celsius, where it stays for several minutes before dropping lower. What is happening during this pause at 0 degrees Celsius? And again, this isn't graded or anything, so take your best guess. No risks here. Seeing answers from most of you, just going to give it 10 more seconds. So again, take a guess if you're not sure. All right, let's take a look. I'm going to hit share, so you should hopefully see a little graph or something on there. The correct answer is C, which is the water is changing from liquid to solid, right? It is going through that phase change, clumping together into a more compact form to be a solid, right? So the energy goes into changing the state, even if it is going in the opposite direction. All righty. Another weird thing in this unit is the terminology referencing the transition from gas to liquid. Often see it and hear it as evaporation, right, is kind of the catch-all phrase. But evaporation actually has a very specific definition. Evaporation is only vaporization occurring in a liquid that is not at its boiling point. It's just occurring on the surface here of the liquid. That's evaporation. Don't confuse that with boiling, which is where you have heated a liquid to the point where usually the heat source is down here on the bottom. And so the water molecules that are liquid on the bottom get so heated and excited that they turn into vapor, and that's what those bubbles are. So that bubbling you see when you're boiling water, that's not oxygen or hydrogen. You're not breaking bonds. You're just creating water in gaseous state that's bubbling out of the water. The catch-all term for all of this is vaporization, right? So the vaporization includes evaporation and boiling all together. So that's kind of the safer term to use for that. Little side note about evaporation and our evolution. The ability to sweat gave us a huge adaptation in terms of human beings and being able to control our body temperature. So, as you know, when you get too hot, you sweat and it cools you down. And the way that works is that evaporation of sweat from your skin is an endothermic process, which means that it's absorbing energy as those liquid molecules that appear on the liquid sweat on your skin, as they turn into gas and float away, they take energy with them. They're absorbing energy, right? They're going from slow liquid to very excited gas, and they take the heat, the energy from your skin. So that's why sweat cools you down, right? If you've ever been sweaty and then a breeze has hit you, which increases the evaporation, you get that very cold feeling because it's removing heat from your skin. And so this, from an evolutionary standpoint, has really allowed humans to be really good endurance athletes, right? We can run marathons. We can't necessarily run super fast compared to other animals, but we can run for a very long time and very persistent, not overheat. Whereas if you look at things like dogs or cheetahs, they actually don't have sweat glands. And so they can run really fast, but only for short periods of time. You're never going to see one of those animals run a marathon anytime soon. And this definitely gave us sort of an evolutionary advantage. But anyway, just kind of cool to see how this applies to things like sweating. We'll apply it to another example in a question soon. So the next concept to understand is vapor pressure. This is a little tricky. The formal definition for it is a force that is exerted above by a gas above a liquid. I find that super confusing. So don't worry too much about that definition. I mean, that's the scientific definition, but what I want you to think about is what I have in red here, okay? Vapor pressure is just a measure of the ability or likelihood that a liquid will vaporize, right? How likely is it to become a gas? And if you have high vapor pressure, that means it's very likely to become a gas. Very easy. It's going to jump from liquid to gas quickly. Whereas if it has low vapor pressure, you're going to need to apply more heat to get it to actually vaporize. And so I'll just show you a graph that hopefully will help explain this. I don't want to confuse you. So note we've got temperature on the bottom. So temperature is increasing, making it hotter going this way. And we've got the actual vapor pressure going up. Now remember, again, the higher the vapor pressure, the more likely it is to become a gas, right? So these ones will turn into gases very easily up here. And the ones down here will have a bit of a harder time. And so just what trend do you notice? Look at all these lines and the shape of them. As temperature increases, what happens to vapor pressure? Does it also increase or decrease? Don't be afraid, little ones. As temperature increases, what's the vapor pressure doing? Look at the shape of the lines.
It's going up.
Very good, right? These are coordinated with each other. So as you increase temperature, you're also going to increase the vapor pressure, which is not surprising, right? We know that if you warm something up, it is going to become a gas, right? Like if we heat up water, it will begin to boil and vaporize. So not surprising there. That's just showing you that. But it's also sort of showing you that things like ethanol and alcohols have very, very high vapor pressures, even at low temperatures, which is why they evaporate really easily. So you'll have two questions that relate to this. Give these a go. They're all about hand sanitizer, which we all have experience with these days. All right, again, if you're not sure, just take a guess. I'm gonna close it down in the next 10 seconds. Okay, let's take a look. Should hopefully see the correct answers now. First question about, let me just jump ahead so I can actually see the questions here. First question was about ethanol, right? Most hand sanitizers are made out of some kind of alcohol. It vaporizes very, very quickly, which means the correct answer is indeed B. It has a very low, or sorry, it should be A, a very high vapor pressure, right? This is because alcohol has a high vapor pressure. It vaporizes very easily. Correct answer was A. And then the next one was your hand feels cold after applying hand sanitizer, right? We all have first-hand experience with this. Get it? But it's because just like sweat, as it evaporates off your hand, it removes heat. And so that's why it feels cold to the touch. Okay, main concept here now. Okay, bear with me. We've been building up to this whole time. Here is the new definition of boiling point. We're going to get scientific here. Okay, we can't just say the boiling point is when water gets to 100 degrees Celsius because that's not really what's happening. Boiling point is defined as the temperature at which vapor pressure is equal to air pressure. Okay, so what you have to imagine again is that vapor pressure is the measurement of how likely a gas is to a liquid is to vaporize, right? So imagine that there's molecules in this liquid that want to escape as a gas, and there's a certain amount of energy they need to achieve that. The problem is that the atmosphere is also pressing down on this liquid. It's pressing down on everything, right? You have air on top of you. Everything has air on top of it. And so they're sort of keeping them in there. And so the energies have to equal out, right? The vapor pressure has to equal the air pressure. And if you can heat up that water to get that vapor pressure higher so that it matches the air pressure, then it can release as a gas. It can begin to boil. Again, I know this is a confusing way to define this and explain it, but just keep that in mind that when vapor pressure is equal to atmospheric pressure or air pressure, that is when you have achieved boiling point. Okay, let's look at an actual diagram of this. What's interesting is that we know that air pressure can change, right? That if you are usually at low elevations, we have a lot of air pressure because there's all this air on top of us, right? But once you go somewhere like the top of Mount Everest, there is a lot less air pressure because there's less air sitting on top of your head. And so this could change the boiling point because, again, vapor pressure is going to have an easier time matching it. And so here's an interesting trend that you will see. Usually at sea level, you experience about 101.3 kilopascals of atmospheric air pressure. That's about 1 atmosphere. We measured 1 ATM. Now, if you were to heat water to just 70 degrees Celsius, notice it's not boiling, right? And that's because the vapor pressure in here has not equaled the atmospheric pressure pressing down on it. But once you hit 100 degrees Celsius, that's when you start to see boiling, right? These liquid molecules now have enough energy to turn into a gas and escape and boil, right? So that's boiling point at sea level. But if you were to go to the top of Mount Everest, there's now a lot less air on top of you. You're at a much higher elevation. There's way less air pressure. And so notice, even just at 70 degrees Celsius, the water will boil. 70 degrees Celsius is just enough energy to allow the vapor pressure of the water to equal the lowered air pressure or atmospheric pressure, and so it will begin to boil. And so even in places like Lake Tahoe or other parts of Nevada that are at high elevation, boiling points are actually a little bit lower because there's less air pressure, and therefore the vapor pressure equals the air pressure much more quickly. So you'll have homework where you'll watch a demonstration of this in the laboratory. So we have a little vacuum chamber in the laboratory. And so I can heat water to about 80 degrees Celsius, stick it in this vacuum changer and use a machine to suck the air out, which decreases the atmosphere, quote unquote, atmospheric pressure around the beaker, and it'll actually boil even just at 80 degrees Celsius. And then the minute I turn it off, it stops boiling. So you'll watch a video of that soon. But this is really relevant to people who like to climb, right? Because it means that water's going to boil a lot faster. You don't have to put as much energy into it when you're at higher elevation because there's less air pressure. Baking at higher altitudes, you actually have to take this into account, right? Because some things will go faster or slower depending on air pressure. Okay, one last question to give a try and see how you're understanding this. All right, looks like answers from most of you. I'll go ahead and share. The correct answer is indeed A. By going to a lower elevation, right? You're now below sea level. Prague is actually below sea level. There's more air on top of you, right? There's more air pressure. And so vapor pressure has to be higher to equal that. So the things are actually going to boil, water would boil a little bit higher than 100 degrees Celsius, has the opposite effect of going to higher elevation. And so this explains that trend. All right. So be honest, what did you think of Nearpod? Somewhat? Yeah, it's a little slower, I feel like, than just showing and giving poll questions. It feels a little faster. So, all right. Any questions or comments on that? All right, kids, your only homework is the Ed puzzle that I mentioned. The only other thing I should mention is that if you can, for our next lesson, I would like you to procure an aluminum can, an empty can. It could be an empty Coke can, empty beer can, empty LaCroix can, doesn't matter to me. But if you have an empty aluminum can, that will be helpful for a little activity we're gonna do. If you can't get one, it's okay. I don't want you like risking your health to go shopping for cans. This is not like a requirement. I'll have an alternative exercise you can do, but that's just something else to watch out for. So, all right, kids, thank you very much. Have a good day.
Thank you.
Thank you.